SwayamPrabha. Digital India. Educated India.
So as I said last time, this should be material which is familiar to those people who have taken some other course on machine learning or have seen something. So this lecture is basically just an overall overview of machine learning. But again, of course, this course was made assuming that people have no background in machine learning also. So don't worry about it. This will just give you an overview of what all machine learning is used for, and it will set the background for what we will do in the next 7 to 8 classes. So last class we saw this idea of having data versus physics models. For whether we are doing forward problems or inverse problem, we need a model for how our inputs or causes are related to outputs or effects. So far in this course and practically throughout your IIT education, we would have seen physics-based models for the most part. But we could also collect historical or experiment data and create data-based models, which is what we are going to see. And one specific example of that is the neural network model. So remember that all forward and inverse problems involve models. So this could be physics-based or data-based. We make data-based models when we have one of the following situations. We either have an incomplete knowledge of physics. I gave you the example of weather prediction. But another case is slightly less complex in that we do know the physics fully. For example, in the case of turbulence, we know that turbulent flows are also governed by Navier-Stokes. But at the resolution that we require, it is difficult to physically create the physics model. In such cases also, we could use data-based models. And finally, the physics itself is simple as in conduction, but it is computationally expensive. Even fin heat transfer is somewhat similar depending on what kind of geometry we are looking at. So these data models can serve as, I use the word surrogate model. Surrogate means substitute. Okay. So the idea is to approximate the actual physics, but do it much faster, as we discussed last class. And these are useful for problems, optimization problems, and inverse problems, as we will see later on in the course. Neural networks are a good framework, okay, within which we can create all data models, and because they satisfy the universal approximation theorem. Again, I'll come back to this point today and a little bit in slightly more detail later next week. Okay. So for the rest of the course, just so that you have a map in the head for what we'll be doing, last 1 or 2 classes will be taken by Professor C. Balaji. He wanted to wrap up, but in the interim, what I'll be covering is 2 sections. One would be for neural networks and inverse problems. Today, I will just do an overview of machine learning. Then April 19th, which is Monday, we'll do learning via gradient descent. It's slightly different to what you have been doing, but it's also related. So you will see something. And gradient descent is a primary algorithm in neural networks. On 20th, we'll look at deep neural networks. 21st, we'll look at something called the backpropagation algorithm. And finally, on 26th, we'll look at inverse problems with ANNs. Of course, there might be some shuffling around here. And we will also do some example problems, except for today. Okay, so today we will not be doing example problems. It will primarily be a PPT based lecture. And of course, you are, as usual, you're welcome to interrupt whenever something is unclear. But starting 19th, we'll start doing in-class problems. Okay. And the second section is on physics-informed neural networks. Last couple of times, I had just probably only 1 lecture for it, but it is becoming very, very important as we go ahead. So I'll spend some more time on this topic. So on 27th and 28th, we'll do physics-informed neural networks for forward problems with an example. And May 3rd and 4th, we'll do physics-informed neural network for inverse problems using some other examples also. So the idea is to do 2 types of inverse solutions using machine learning or neural networks. One is, this is a data-based approach. This is what I'll call a hybrid approach. Uses both data as well as physics. Okay, so we will see these. in the next. This is basically sort of the curriculum for or the syllabus for the rest of the course as far as machine learning is concerned. And after that, Professor Balaji will do 1 or 2 classes. So I'll very quickly sort of rush through an overview of AI and ML. Again, forgive me if you are already familiar with this kind of material. So we would have seen multiple use cases in real life. Now we have our spam detectors within our, let's say, Gmail inboxes. You have Amazon Echo, which is primarily a speech recognition system and a query based system. Then we have this Amazon's recommendation engine. We used to have, I do not know whether Google still uses this. There was this Nexus, which is a self-driving car. Of course, Tesla is very famous. It's a self-driving car. So the general simplistic definition, which is what I'll be doing within this course, is AI and ML. ML stands for machine learning, AI stands for artificial intelligence. We try to replicate activities which usually require human cognition. So usually you look at an email and you can quickly say whether it is spam or not, and it's kind of hard for you to articulate what those rules are. Of course, these kind of general algorithms have now are being increasingly used in other fields, such as trying to diagnose automatically. In fact, a colleague and I are working on trying to automatically detect COVID using X-rays, etc., etc. So wherever radiologists, specialist radiologists were required, you can start using the same techniques elsewhere. And of course, within our course, we'll be doing this for fluid dynamics, heat transfer. Okay, so whatever we were doing using, let's say, ANSYS Fluent, can we do that using machine learning? So the possibilities are tremendous. Much like the computer revolution, you now have the AI revolution. So before the computer revolution, even if you read sort of science fiction novels from those days, you will say that they still had a limited idea of how computers would basically subsume everything. For example, speech, I'm not just talking about AI, the fact that we can stream audio, we can stream video, we can do everything that multiple devices were doing is simply due to a understanding that everything analog can be finally converted into something digital. Okay, so that one thing which we reduce everything to zeros and ones has made the current computer revolution possible. And similarly, at the algorithmic level, just like there are zeros and ones for information, can we have some universal algorithms that can cover all possible algorithms? And that's what AI and ML are basically trying to reach. Okay, so there are 2 levels of AI. One is called weak AI. Again, all this is not really important for this course, but I just wanted to introduce you to this since we are doing ML anyway. So this solves narrow problems. For example, something like Siri or Amazon Echo, etc. This can do specific activities. So as I was saying this, it's quite funny. I wish I could show you this. Let me see if I can. In fact, it's a nice example by itself.
This may not be a big surprise, but I'm an Apple fan.
So I'm not sure if this is visible. I'm not sure if you can see it. I'm near my current laptop is actually a Mac. And the moment I said Siri, it started up by itself and it started transcribing whatever I was telling you. So this is both the advantage and the disadvantage of these automatic systems. So this is a speech recognition system, as all of you know, and it got triggered by me just saying Siri there. Okay. So this is an example of a weak AI. You can see it's quite dumb. It doesn't know that I'm not talking to it, but it has been created for the specific purpose of recognizing speech and transcribing it, and maybe doing some backend searches and giving us some output based on that. Okay. So it solves narrow problems, and people will contend this, but I see even Google searches as weak AI. Basically, you have some rules-based thing. More importantly, what people are trying for, let's say OpenAI is trying for, is something called strong or general intelligence. It should be able to adaptively, intelligently be able to do both search as well as just like human beings do. Okay, answer not just specific questions and not just take care of specific domains, but be able to do general things. Are there examples of that? There are none. Only in movies you have some such examples. So typically we are only constrained with weak AI. Okay. So weak AI is what we are going to look at. But then how are weak AI programs generated? There are two basic historic approaches. One is rules-based algorithms. All of us are familiar with this. This was earlier called expert systems. Idea is to list all the rules which govern a particular field. So to give you an example, if I have what I will call, again, like I said, even faculty here will disagree with me, but let's just go with what I'm saying. Let's call a rules-based algorithm as weak AI. So if I have something like a software which solves for heat transfer, and I am giving it that conserve mass, conserve energy, conserve momentum, it's a weak AI kind of paradigm, or it's a rules-based paradigm. The moment you give these rules, it's going to behave in one and only specifically one way. Okay, so that's a rules-based algorithm. You could even give rules for example, spam. So you could say if you see the word bank, Nigeria, etc., then mark it as spam. This is how earlier spam-based algorithms worked. And as you can see, the number of rules that you have to give will expand very, very quickly. Okay, so you will not be able to write down all the rules. How do we walk? How do we speak? How do we recognize our friend? How do we recognize a dog? If you try to list it into a finite set of rules, you will see that quickly the number of rules start exploding. Too many exceptions, so you can't program it. Another problem is that rules-based programs don't learn. Okay, sorry. They don't learn. What I mean by that is, so if I have, let's say, ANSYS or something like I said, a spam recognizer, in case you have a bad example, you can't give feedback to the program and say, hey, change the program, this is bad. Some human being has to come, look at these exceptions and then change them again and again and then manage this. Okay. So as against that, we have learning based algorithm, and this is what we call machine learning. And this is where we are going to focus our attention, and even within that, a very small subset. Okay. So typically machine learning is a small subset of AI. The idea is to observe data and learn from the rules. Okay. Learn the rules from the examples. Sorry. So for example, if you are bicycling, the only way to teach somebody bicycling is to say, get on the cycle, you kind of hold that person, and when that person falls or loses balance, they implicitly learn something. So typically learning is implicit here, and we can't quite articulate what has happened. Okay. How do we recognize a face? How do we recognize a voice, etc., etc. Okay. The problem, of course, is if I don't give rules and I am giving only data, obviously you need a lot of data. So just to give you an example that I will repeat again, suppose I say my input is 1 means the output is 2. I'll say, and if I ask you what is the relationship between input and output, it could be infinite relationships. Okay, could be x plus 1 is y, 2x is y. Now suppose I say input is 2 and output is 4. Now you might start thinking our pattern recognition system kicks in and it says, okay, it's 2x. But even that need not be the case, because I could fix a nonlinear function with greater variables. So I could say output for 3 is 5, and I can keep on adding inputs and outputs, and you'll have to keep on adjusting your function in order to kind of fit it. Okay. So the problem, of course, is it needs a lot of data. If you have very few data, it leads to a problem called bias. Okay. So I will not. Last couple of years, I used to cover this in greater detail, but I'll just kind of indicate to you. This is very similar to seeing a few people and generalizing. Okay, oh, this person from this community will be like this only. So that is an example of very little data, lot of bias. Okay, so this is a problem with AI, and we will see later on when we come to doing something like machine learning with or ANNs on even heat transfer problems. We have the same problem in that you have to add a lot of data for in order for it to understand what you are trying to say, what is the implicit rule here. Okay. So there are, of course, many current applications which find ways, even including Google search, which mixes some rules-based algorithms, their old algorithms, with learning-based, ML-based algorithms today. Okay. So here is the overall terms we tend to use. AI is the large field, machine learning is a smaller field within it, and deep learning, which is what we will be looking at, is the thing inside. We also tend to, you can say that neural networks are a part of deep learning. Okay. So what is machine learning? Machine learning is not, of course, all of us know, somebody sitting and reading a book, or a machine sitting and reading a book and understanding it. It is actually using data in order to answer questions. More sophisticatedly, it's the study of computer algorithms. That the key word here is this: they have to improve automatically. Like I said, with a spam detector, when I give new mails, you would have seen this in Gmail also. When you give a new mail and say this is not spam, it is learning something extra. Okay. So the idea is to study of computer algorithms that improve automatically through experience. Experience simply means more data. Okay. The formal definition of machine learning is that a computer program is said to learn from experience if, for a specified set of tasks, it improves its performance if you give it more examples. So idea is this: for some specified task T, for example, I could say I want prediction of heat transfer, or I want prediction of drag. That would be the specified task. We should say that as experience, as data increases, that's what I'm calling experience in their language. As data increases, performance P should increase. Okay. We will see how this language can be precisely, exactly in the usual way applied to linear regression also. Okay. So you'll see it. I'll probably do it later in today's class itself. Okay. So this general application, general definition applies to even things like linear regression. Okay. So the idea is this: there is a paradigm shift in machine learning. I don't quite like this diagram, but this is used a lot by even people who are very influential in the machine learning community. So I will reuse it. So the idea is this: in classical programming, we take in data, we take in rules, and we give out answers. So let me give you an example which will make this clear. Okay. So I could take in, for example, data would be email. Okay. Give me an email. Give me the rules which determine whether this spam or not. Okay. So just to give you a simple example, if there are a lot of misspelled words, then it is spam. Let's say there is one such rule. And the answer you want is spam or not. Okay. So these rules are specified by the programmer. Okay, so you have to pre-specify the programmer has to pre-specify the rules. Okay. Another example, let's come to heat transfer. Suppose I give you data which could be location, time, or grid points. If I have something like this, you have to give me rules. The way I'll give you rules, if you have done CFDs, I'll give you the governing equations, discretize them, and I'll say, okay, the relationship between grid point I and I plus 1 is so on and so forth. Or in some way, let us say we are doing an analytical solution. You give me the location, I have a formula. T is linear. Okay, I have an expression which will tell you the answer. The answer required, let's say, is the amount of heat transfer at the base. So that would be traditional classical programming, rules based. Machine learning, on the other hand, works in the opposite way, which is you give me data. Let's take the email example. Again, the same thing. Give me email. Give me answers. For a bunch of emails, you tell me spam or not. Okay. And here I infer the rules. Okay. So you can see, in some sense, this is also like an inverse problem. Okay. So if you see, this is a forward problem. Classical programming is a forward problem, and machine learning itself is an inverse problem in itself. Okay. So the idea is, I give you the email, I give you the answers. After having seen a bunch of these, can you tell me what were the rules? Okay. How do I determine? And after that, after you have learned the rules, then you do a simple classical program to run it. And as I told you, the reason we use it is sometimes the rules are very hard to infer or for you to understand explicitly. So this is learned implicitly through this idea of giving both data and answers. So for example, this was one of these spam mails last year, which came to my inbox. And you can see that if you read the mail, you will see it doesn't give you any of those misspelled things, etc. So if you create explicit rules, the problem is people will hack it and try and write a different kind of email, for example, for spam, and they will bypass your spam filter. Okay. So the idea is, the moment I give this, I will mark it as spam, and it has to improve my rules. Okay, so it's a new example. And once I give the new example, it should somehow improve my rules so that such mistakes do not happen in the future. Okay. So machine learning is useful in multiple places. I will actually skip this thing because we are specifically looking at a heat transfer example. But something I do wish to say is, when you need the solution to adapt to very specific cases. Okay, so for example, you have a specific type of room or a specific type of automobile, and you want very specific type of HVAC there. Machine learning is the kind of thing which can adapt very quickly to such situations, and that's where the future promise of ML is extremely strong over the next 10, 15, 20 years. Okay. There are two types of approach. Again, this is not particularly important for our class, but I'll just mention it. So supervised learning means just like the spam or not spam example that I just gave you. So what we do is we take each example and tell you input and output are both given for examples. Okay. So for example, you give a mail and you also tell it this is spam or not spam. You give an image, you tell the machine whether this was cat or dog, and you keep on doing this over multiple examples. Then finally, when you give a new example, the machine is supposed to figure out was this cat or a dog, was this email spam or not spam. This is one type of learning. This is called supervised learning. Okay. Another type of learning is something called unsupervised learning. Now imagine unsupervised learning will be like this. I have my email again. I'll use that example because all of us are familiar with it. And I just give it all my emails. I don't tell that some were spam and some were not spam. Now what it is supposed to figure out is that it is supposed to separate emails into two classes and say, well, this is one type of email which shows one type of patterns, and this is another type of email which shows another type of patterns. That is like this. Okay, this is one type of points, this is another type of points. Now it might not know to call it, of course it won't know to call it spam or not spam, but it knows enough to cluster it. Okay, it sort of knows how to group data. This is not the only unsupervised learning task, but there are multiple such tasks. But all you do with unsupervised learning is you just dump data stream, okay, and it is supposed to figure out. For example, we all, even when we are children, we will probably be able to distinguish different colors through our eyes. We know that this looks different from that, but we do not know what to call it. We don't know how to point to it, but we know that this is one group of colors, that's another group of colors. So something similar could be used. For example, if you have data within heat transfer or within fluid mechanics, maybe, I mean, no machine has done this so far, and unsupervised equivalent would be, okay, this flow looks like one type for laminar flow, and that flow looks like another type for turbulent flow, and I should probably be doing something different. This is a possibility with machine learning, okay, if you use unsupervised learning. There are multiple other types of learning approaches. All of them are a mix of some supervised, some unsupervised. I will not go into that. I'll just say that even within our lab, we are trying something called self-supervised learning. but we'll come to that probably end of this course at some point. I'm going to skip it. Okay, so I talked about this idea of having this machine learning paradigm where you learn the rules. So how do we do it? It's a very, very simple idea. I'll just come to that in the next few slides. So before we do that, and even though this is not important to us within this course, I'll just mention it, because what we will be doing for heat transfer can be done for images, can be done for audio signals, it can be done for everything. So what is it that makes it work? This is the kind of generalization which, like I said, any signal can be turned into zeros and ones. So we are going to do something very similar here. Okay. So the basic idea behind ML is the idea that every problem that you can pose can be posed as a data problem. Okay. And every solution can be thought of as a function or a map. This is one type of approach in machine learning. Okay. So for example, you are seeing images and you want to say, is this a cat or a dog? Just to give you, or does this person have cancer or not cancer? Just to give you an example. So we get images as some qualitative things, but for a machine, it is just numbers. Okay. So what you need to do for every machine learning problem is to somehow turn whatever you think of as an input into a number. When you see an email, you should be able to digitally turn it into a number. There are multiple ways of doing it. One simple way is to rank all the words in a dictionary. The word A would be corresponding to one. The word AB could be corresponding to something else, etc. And you just turn it into a string of numbers. So convert input into numbers. This we call input vectors. Similarly, output we turn into another numbers. For example, instead of saying spam or not spam, I could say 0 and 1. Okay. So idea is the machine only knows to map numbers to numbers, and the machine only knows how to process numbers. It doesn't know really how to process images or even sounds. You can do that only if you convert it digitally into some number format. Now, how you do it depends on your cleverness, and that can make the problem easy or difficult. Okay. So appropriate inputs, how to convert it is an essential part of the process. I can't emphasize this enough. People de-emphasize this too much, but this is where a lot of your engineering know-how comes. Okay, your cleverness, in fact, if you see all recent algorithms, a lot of cleverness comes here. Okay, how you pose the problem. Okay. So the learning task often is simply finding out a map. As I showed you, 1 gives you 2, 2 gives you 4. We have seen this right from childhood. So effectively what we are doing is, for large sets of data, we are simply mapping inputs to outputs. That is the fundamental trick which first makes ML possible. Okay. So remember, we had this machine learning paradigm. Okay. So let's look at it in some detail. Okay. So the input data X comes, and I have also given output data Y. Again, let's take the example, email, spam or not. Geometry and other inputs, and we want to know heat transfer. So the machine learning is supposed to relate X and Y. Okay. Now, once we know that there is one set of numbers Y and another set of numbers X, mathematically the way to relate these two is to say Y is a function of X, where F means an actual mathematical function. Okay. So this function in machine learning is called the hypothesis function. Okay. So often labeled as, sometimes we say Y hat is H of X. Y hat, why am I putting this hat? Because that is not the actual output. This is the output that will come when I put a mathematical function there. This will become clearer as we go through the next few classes. H stands for hypothesis. So H is an approximation to my original F, and it's a surrogate to the original F. F is the actual function relating X and Y. I am going to guess, and I am going to get some approximation, which is going to be H of X. Okay, just 1 second. So this function, every function has two parts, the form of the function. For example, I could say something like this H of X is linear, and let's say input X had two variables, X1 and X2. I could say something like h of x, let us say is w0 plus w1 x1 plus w2 x2, and I have given another example plus w3 x1 x2. So this is the example of a form of a function. Another thing is the parameter of the function. What is meant by parameter? These things. Okay, so two things are unknown. What does the function look like, and what are the constants within the function? What are the parameters within the function? Okay, so when we say machine learning is learning, machine learning is learning only the parameters. It's not learning the form of the function. This is very important. So when I say I am learning the rules, what I am learning is simply the parameters. Sorry, 1 second. So the output which I called rules were simply the parameters. The form is provided by us and it requires some amount of domain knowledge. Only then can you go ahead with it. Okay. So this modeling process of finding the parameters involves 2 steps. It's exactly the same as what you did with inverse problems, and you will now be able to see the connection a little bit. Okay. So remember, for an inverse problem, you do the forward pass and then you improve the parameters. So forward modeling is like this. Suppose you give me x and you give me some set of parameters w, okay, and we have made an educated guess at what the function looks like. Let's take the example of our slab. There is some temperature here, some temperature here. We do not know what those are, and we have some measured temperatures in the middle. So we will make an educated guess that the temperature profile here, let's say is T is equal to some linear function w0 plus w1x. So this is a guess. How do we guess? In some cases we explicitly have a data model, and in some places we simply have an educated guess, and I'll come to a more bigger generalization, which is neural networks, a little bit later. Okay. So when we say a hypothesis function, it is simply a guess at what the function looks like. So you have the form of the function, linear, quadratic, you saw exponential in some cases, for example, for the fin example. Okay. And of course, we have to tell you the parameters. So if I say it is e power mx, I have to tell you what m is to. Okay. So we sometimes in machine learning use this notation, y is f of x, and we put a semicolon w. What that means is f determines the form, w determines the parameters. Okay. Now suppose I give you x and I give you w and I also give you f. Of course, you can find out a corresponding y. Okay. So this function going from the cause to the effect is called the forward model. Okay. And w are the parameters. Okay. It's also called feed forward. 1 second. But this will only take you for a given set of parameters. It will take you from input to output, but we want to learn the parameters w. Okay. So the idea is very simple. Again, the same example that I gave you. Collect input vector, output vector. For example, collect location, temperature. Collect email, spam or not. Keep on collecting this. Okay. This we will call the ground truth. Ground truth means the truth that we have observed on the ground. Now, from here, you guess the form of the hypothesis function. So, for example, you say w0 plus w1x1 plus w2x2 or a linear function. Now, take an arbitrary guess. This is different from what you did for regression. Up until here, it is very much like regression. Okay. But then we solved for w directly, okay, based on the least square principle. And you will see that we are going to do something very, very similar even in machine learning. But what we do is we take an arbitrary guess for w. Okay, so you make a guess for w, give some w. You will get some output. Okay, and this is the output due to your hypothesis. Typically, what will happen? These two will not match. Okay. Obviously, you took an arbitrary guess for w. Why should it match? What we do is we define a cost function. It is the same as the objective function that we saw so far. We say if y and y hat are not the same, give me a cost. Typically, we use least square. Now, what we do is we specify this problem now as an optimization problem. We say find an optimal W which will minimize this cost. For what? For all the examples that I have given so far. So this is very much like the least square problem. Okay. But what we are going to do is we are going to solve this problem iteratively, and I'll come later in next week for why we do it iteratively and why not do it directly. Okay. So we usually solve this, and the iterative procedure is what is called gradient descent. Okay. This is the most common machine learning optimization algorithm called gradient descent. In case you have done optimization courses, you will know that there are others possible. Okay. Other optimization algorithms are possible. Okay. One second. So the basic idea is this: do a feed forward, improve your parameter by iteration, and this is very similar to many of the iterative algorithms that you would have done even within this course. Okay. So two main ideas. You can convert even qualitative problems into data problems by simply converting them into numbers. So this is what allows for applications in heat transfer also. For example, you simply have an image and you want to use that as one particular input, you can use this idea. And we collect data as input-output pairs. You provide a hypothesis function and you improve the parameters based on mathematical feedback via the objective or the loss function. So what I'll do in this final 10 minutes is try to give you a basic idea of how we can relate what you did with linear regression with a neural network, and then we'll dive into deeper details over the next 3 classes. Are there any questions so far? Questions? Okay. If not, I will just move ahead. I just want to show you a linear regression example as a learning problem. Okay. All of you are familiar with linear regression. So this gives you some chance to see mild details. I'm not going to give you a lot of details. I'll give you detail in the next week. And I want, my basic purpose here is to introduce you to the neural network and show you how closely it is related to what we have seen as the linear model. Okay. So this I'm going to skip. So here is an example. You can see this also as I am giving you a house price example because this is what is commonly used in machine learning. Idea is simple. You have the area of the house. You have a price of the house. You have a lot of such data. It throws away a lot of important things like how many bedrooms, etc. But even with this, you can see roughly that the price increases as you increase the area. Okay. So the question would be, the regression question would be, given the leaving area, this is simply, remember, this is still a forward problem. I have not yet come to the inverse problem. Forward problem is, can you relate cause to effect? Okay, why am I doing that? I might know the physics, no, and that's why I gave you the example earlier. What happens if you don't know the physics? Okay. In such cases, you will have to treat it as a purely data problem and say, can you first relate the cause to the effect, and then I will relate the effect to the cause as an inverse problem. Okay. So given the living area, can you predict the price? Once again, input vectors X could be area, it could be an image, it could be an email, it could be a geometry. And output, corresponding output would be for the area, the price. For the image, is it cat, dog, whatever it is, email, is it spam or not spam? And geometry would be, can you give me heat transfer? Okay, you train over many example sets. Okay. Once again, same thing. In this case, we are going to take a simple model, the linear model. We are going to say W0 plus W1x. And the parameters are what? Find out W0, W1. How are we going to do it? We are going to minimize least squares. All of us know that the appropriate cost function here is simply taking the square of the difference between our model and the actual data, adding it, taking mean. Okay. So suppose the way I will do it is, suppose I give a very bad W0 and W1. Okay, if I give W0 as 150 and W1 is 0, This is what it looks like. What we do is we improve this through an optimization algorithm, which is what we call gradient descent. Instead of directly finding out W0, W1 by that least square formula that all of you would have used by analytically optimizing it, we optimize it using a iterative technique. This is just like the difference between, let us say, using Kramer's rule for a system of equations versus using Gauss-Seidel. Gauss-Seidel is iterative, you have to give an initial guess. Kramer's rule is deterministic, you give one shot answer. Okay. So learning here means I am going to improve based on each shot. I'll give a guess for W0, W1. It will give me some line. Based on the amount of cost function I am getting, I am going to improve. So this is what we do. We constantly improve and we get some final answer. So this key step of going from one guess for W0s to an improved guess is what we call learning in machine learning. And I'll show you gradient descent on Monday. Okay, so this is the final answer. And the parameters now we have are the optimal parameters that are now ready to deploy. If somebody gives a new point here for 3,500 feet, what is the cost? You will say roughly the cost is this. With, of course, if you are doing a Bayesian thing, you can give some uncertainty in the cost too. Okay, I'm going to skip this. Now the question, of course, is I gave you a linear function. What happens if I don't know any function and it looks really, really messy? Is there one general model which can approximate any function? And the answer for that is neural networks. So I will now go from our linear model to the neural network model. Okay. The linear model looks like this. Remember, simple idea, W0 plus W1x. And what I am going to do now is to represent this diagrammatically. So let's say the input is X, the output is Y. I want to go from the input to the output. What am I doing to this? I am multiplying the input by W1. Okay. This is called a weight, or I call it a parameter. This is, let's call this a weight. What happened to W0? I will add 1 multiplied by W0. This is usually called the bias unit in the machine learning literature. Okay. Remember, I am doing nothing new. I am simply representing whatever we saw so far as a diagram. This sigma is simply sum the two, I get the output. This is a linear model. This is just a diagrammatic representation of the linear model. Now let's look at the neural network model, which is a small change. Genuinely, it's only a small change above the linear model. Okay. Now, if you see, if I take, I will call this a neuron now. If I take this neuron, it takes an input from this. Okay. You can see these lines going from here to here. So the idea is the same. What do? I take whatever value is here. If I have x1 here, I'll multiply it by w1. If I have x2 here, I'll multiply it by w2. Do all that and sum it up. Okay. Here on this side, we are going to do the same thing here. Simply do sigma of wi xi. But there is a small twist. We add, after I do sigma of wi xi, after that I pass it through another function which is non-linear. So instead of saying A is sigma of wi xi, I say A is g of sigma wi xi. Okay, that is it. Okay, nothing, no other major change over the linear model. Take the linear function, run it through a non-linear function. Okay, so every neuron has a linear and a non-linear operation. The linear operation operates on a vector of inputs, just does wi xi, and the non-linear operation already works only on a scalar. It takes a scalar function in and gives another scalar output out. That is it. So A is the neuron, sigma is the linear operation, and G is the non-linear operation. Okay. A very standard function that we use, a non-linear function that we use, is called the sigmoid function. Okay. It looks like this. Okay. 1 by 1 plus e to the power minus x. It goes to 0 if the input is very negative. It goes to 1 if the input is very positive. And in between, it just moves smoothly from here to here. Now, some of you might kind of intuit that this looks like the approximation of a step function. Okay. It's a smooth approximation of the step function, what it is supposed to represent. Now, I'll give this brain analogy only once here because it's not precise and that's not really how things work. But anyway, we will talk about it just for this couple of minutes. The idea is this: each one of these blocks are supposed to represent neurons. For example, let's say you saw an image. Let's say each pixel activated some neuron in your brain. And that neuron is connected to other neurons, which is connected to other neurons. And finally, this is the output. Okay, some output neuron will say, and you will recognize, yeah, this is a cat. Okay. The idea is this, that the neuron doesn't get activated unless there is sufficient shaking. For example, you are sleeping, somebody is shaking you. After somebody shakes you heavily, you wake up. So this is often, this A is called the activation function. Oh, sorry, this G is called the activation function. A is called the activation. This is activation function. The idea is this: only if it is sufficiently heavy will the neuron fire. Okay. And now, which all neurons fire put together decide the output. This is the rough abstract model on we decide this. But what is actually making it work mathematically is this idea of the universal approximation theorem. The idea is this: if you give me sufficient data and if you give me sufficient number of neurons, okay, a neural network, this is called a neural network. You can see that this is simply a function. Why? Just like this is just a diagrammatic representation of a mathematical function. Just like we showed the linear function as a diagram, I am showing a non-linear function as a diagram. So you have some g of wixi, this will be g of wixi, etc., etc. This will have three g's, g of wixi. You can see that this is going to look like a complicated function. But there is this theorem which says that even if you have only one layer, now you can see I call these things something. This is called the input layer. This is where we give all our inputs. Output layer, this is where we collect all our outputs. In between, these are just computational layers in order to create newer and newer functions. Those are called hidden layers because we only know the input, we only know the output. It's very similar to how our brain works. I only know I saw the cat and I simply said cat. I don't know what all processing went down inside in my brain. So this is that hidden processing and it's called the hidden layer. Okay. It's hidden in the sense that it is neither the input nor the output. It is some intermediate calculating layer. So what we know is that for given sufficient data and neurons, a neural network can approximate any function to any desired accuracy. Okay. So this is basically the heart of deep learning. You give lots of data, you give lots of neurons, you give lots of layers, there will be lots of learning. Okay. So that is it. This is the rough paradigm through which we will be working. Give me XY pairs. Let's give a hypothesis function. Typically, we'll give a neural network as a hypothesis function because it can approximate any function. Okay. Give an arbitrary set of guesses. You can see here that there will be lots of guesses you will have to give because there are lots of weights. Okay. So define a cost function. For our application, we'll be typically using only the least square cost function and then find out optimal W. Okay. Even very complicated neural networks effectively work in a very similar fashion. If you see a language model, you see YouTube transcription, you see face recognition, you see speech recognition, something, this kind of unit is very, very, very important and it's sitting there at multiple places. Okay, so this is how even a spam detector is working in the same way. Okay, one final slide. We have to, as engineers, we have to provide lots of things. Appropriate input and output vectors, appropriate data sets, some appropriate form of the forward model. For example, if you are, even if you choose a neural network, how many layers, how many neurons, okay, what is the loss function? Typically we use least square. What is the optimization algorithm we are going to use? I will just discuss gradient descent, but you could use Liebenberg-Marquardt or something of that sort. Okay, so this is not magic. It requires a lot of input from the engineer. Okay, so I'll just stop here. The general procedure for anything that we will be doing will involve the same process, and we'll get into the details of what this process is starting from the next class. Thank you. If you have any questions, I am available here for this. Okay. If there are no questions, thank you very much.